Oh, welcome back to qualitative graphing of polynomial functions. We're moving on to the next exercise, number 3. The function gx has the following features. It has an absolute minimum at -3, -50. So I will highlight the information. So this would be an ordinary point on the graph of a function, but it would also be a point that marks where a function is changing from decreasing to increasing. Because when a function hits a minimum, then it goes from decreasing to increasing. So at x equals -3. Now, g of x is negative between -4 and -1, x values between -4 and -1. Now, this is a very important piece of information, and it would be my starting point in drawing the graph. So always whenever you draw these type or answer these type of questions, look for the intervals where function is positive or negative, because the endpoints in the interval will serve as the x-intercepts, because as we have explained in class, when a function goes from negative to positive, it must pass through 0, providing that the function is continuous, right? And polynomial functions are continuous. Similarly, from positive to negative, it has to pass through 0. Now, from what I see in here, so the endpoints are at -4 and -1. So these two endpoints translate to x-intercepts for the graph of the function. So I'll write this down so I see it. And when I see it, I know how to put it on the graph. Okay, and it has a second order root at x equals 2. So there goes another x-intercept. And we're also given that the x-intercept at 2 will be a second order x-intercept. So what does that mean again? It means that the factors for first order here would be x plus 4 and x plus 1. And for first order, we'll have the factor of x minus 2 raised to the power of 2. So we have to sketch the graph of the polynomial function and then write a possible equation. So we're doing them simultaneously in a way. So I'm going to focus now on the intercepts. So here are the intercepts at +4, -4, -1, and +2. So we will sketch we will scale the axis in here. So x -4 is right here, -1 right here, and we have x at 2. So here we are, 1, 2, 3 zeros. Now, since the order of the graph of this function appears to be 1 plus 1 plus 2, we'll say that this is most likely a 4th degree polynomial function. So we are not told that what the order of these other intercepts are, because sometimes it may turn into other shapes like inflection points. But because we are only given one interval where the function is negative, from -4 to -1, then we'll keep these roots as the first order roots for now. So it has a minimum at -350. So we'll make that clear in here. So at -3, and I'm gonna call this 50 negative. So at -350, we're gonna have the graph passing through this point. And now we have to start sketching the graph. So I'm gonna start off with drawing the graph from quadrant 2, and I'll make sure to hit the x-intercept at -4. This is turning straight. I don't want that, so I have to change it. So polynomial graphs are very curvy, right? So, and here we go. We get our minimum point. At x equals -1, the function is still negative. Now remember, being negative means below the x-axis, right? I'm going to write this down here. And if there are things that you mix up, or concepts or ideas that you mix up, write them down, because when we write things down, we see them better. And we're going to hit the positives now. and will never come back into the negatives because we don't have other intervals where the function is negative. And not only that, but when we come closer to x equals 2, which is the second root, we have to make sure that we approach in such a way that we're able to make a nice smooth turn in there because we have a turning point. So this would be a possible graph of this polynomial function. And we're going to say this is, or it seems like a fourth degree polynomial. I'm going to write the equation here, g of x equals, oh, let's make this purple, x plus 4, and then x plus 1, and then x minus 2 to the power of 2. So we know that this function can stretch at some point, so it would have some coefficient a. And I want you to pause for a second and think, would it be possible in this particular example to be able to find the value of coefficient a? So would that work? Okay, so let's think about it. In order to find a specific member in the family of functions, we need to determine the stretch or the coefficient a, the leading coefficient. And as you can see in here, we are given the coordinates of a point. And to find the coefficient a, all we need is any point on the graph of the function. Now, any point would do the job. Y-intercept is the more convenient if given. That's because at the y-intercept x equals 0, so it makes the substitution easy. But any other point would work except for the x-intercepts. So substituting back the x-intercepts in the equation of the function would not allow us to find the coefficient a, because then we're going to get, a 0. So we're going to get zeros for all these factors. So to find a, we have to divide by 0 here. You get the idea. And if you don't try to use the x-intercept in finding coefficient a, and you will see whether or not it works and why it doesn't. Long story short, here is our equation. And our mission now is to find the coefficient a. And the way we're going to do this is by using this beautiful little point here, -3, -50. So x now is -3. And when that happens, the y value will be -50. So we have -50 equals a, -3 plus 4, -3 plus 1, and then -3 minus 2 squared. So -50 equals a, 1, -2, -5 squared is 25. So we get -50 equals -50a, which tells us that the coefficient a equals 1. And now we can say with confidence that the equation of this particular function, gx, is 1, x plus 4, x plus 1, x minus 2 squared. All right, so in some occasions, you will see that the question may give you the information, all this information, and then you will be asked to find the coefficient a and the equation. So the equation of the function and the specific member of this function, so the exact equation. Now, if that was given right at the beginning, that may make you feel probably, and this is an assumption I'm making, and I hope I'm wrong, it makes us less confident because we think that there is so much to find with so little. So always take the steps one at a time and use any strategy to actually approach the solution. And that whether that could be graphing the function or creating an equation, not just the exact equation. And then as we get closer to the solution, the more we work with the function, the more we get to know it, and the better we'll be at determining the right strategy to answer any specific question there. All right, I hope that was helpful. This was helpful, and I will continue with the next videos in this handout. Just stay tuned. Bye for now.